let's get started. So, what is work? Well, most people would say they are working when they do anything that requires a physical or a mental effort. Now, in scientific terms, work is the use of force to move an object a certain distance. More specifically, to do work on an object, some part of the force you exert must be in the same direction as the object's motion. Let's look at the following two examples. On the left side, Norbert is lifting a stack of textbooks from the floor. And on the right side, he is carrying the stack of textbooks. Note the direction of the applied force and motion for each example. In which example is Norbert actually doing work? If you said the left side, you are correct. Why isn't Norbert doing work in the example on the right? Well, because no part of the applied force is in the same direction as the object's motion. When the force is in the same direction as the motion, we can determine the amount of work being done on an object by multiplying force times distance. What are the units for work? You know that force is measured in newtons, and distance can be measured in meters. The product of a force measured in newtons and the distance measured in meters is a measurement called a Newton meter, or the joule. The joule is the standard unit used to measure work. 1 joule of work is done when a force of 1 Newton moves an object 1 meter. Do you have any idea how much a joule of work is? I know. Let's take an apple, which weighs about 1 Newton. Now, if you lift the apple from the floor to your waist, which is about 1 meter, you do 1 joule of work on the apple. But what happens if I want to lift 100 apples? For me, that would take a lot of force, and I don't think I have enough energy to do that. Let's go back to our example with the apple. Now, I easily have enough energy to lift this apple from the floor to my waist, and I know I'm doing work on the apple as I lift it. So there must be a relationship between work and energy, right? When I lifted the apple from the floor, I caused a change. In this case, the change is in the position of the apple. An object that has energy has the ability to cause change, or the ability to do work. When I worked on the apple, some of my energy was transferred to the apple. You can think of work then as the transfer of energy. As I lifted the apple from the floor to my waist, the apple gained energy. Let's focus on 2 forms of energy: potential energy and kinetic energy. Let's take a look at each. If I hold the apple still in my hand, does the apple have energy? Careful, not all forms of energy involve movement. Well, this apple has stored energy. We call it potential energy. Holding the apple like this gives the apple the potential to fall to the ground. Now, if I release the apple falls. The potential energy changes into kinetic energy. It is pretty obvious when an object has kinetic energy. As long as the object is moving, it's said to have kinetic energy. What's more difficult to determine is how much potential energy an object has. Let's go back to our example with the apple. The potential energy of this apple really depends on height. How high or low my hand is from the ground. We call this type of potential energy gravitational potential energy. Gravitational potential energy depends on mass, gravitational acceleration, and height. Near the Earth's surface, gravitational potential energy, or GPE, is equal to the product of mass, gravitational acceleration, and height. Remember that G is the acceleration caused by Earth's gravity, which at sea level equals 9.8 meters per second squared. Let me show you an example. Suppose a satellite has a mass of 293 kilograms and we lift it to the top of Mount Everest. What is the gravitational potential energy of the satellite? Well, what do we know? We know mass is equal to 293 kilograms. Gravitational acceleration is equal to 9.8 meters per second squared. And we know the height of Mount Everest, which is approximately 8,850 meters. Let's write the equation for gravitational potential energy. GPE equals mgh. Substituting in our values for mass, acceleration due to gravity, and height, we get GPE equals the product of 293 kilograms, 9.8 meters per second squared, and 8,850 meters. The answer turns out to be approximately 25 million. Don't forget, I need to assign a unit to that number. Units are very important when explaining scientific concepts. Do you have any idea what the unit for energy is? Let's figure it out. The original equation for GPE is mgh. Mass times gravity is equal to weight. And weight is measured in newtons. Remember, weight is a force. Therefore, the unit for gravitational potential energy is the Newton meter. Do you remember from earlier in the program what a Newton meter is equivalent to? Well, if you said 1 joule, you're on the ball. 1 Newton meter is equivalent to 1 joule. Wait a minute. Work is also measured in joules. I think we just showed mathematically how energy and work are related to each other. Now let's go back to kinetic energy. How much kinetic energy do you think an object, say, like a rocket, depends on? The kinetic energy of an object depends on both its mass and its velocity. The mathematical relationship between kinetic energy, mass, and velocity is Ke equals 1/2 mv squared. Notice that the velocity is squared in the equation. Remember, guys, the number 2 is called an exponent. The exponent. So, are you ready to try a problem involving kinetic energy? Here's one for you. Norbert's Mars rover, with a mass of 210 kilograms, is traveling on the surface of Mars at a speed of 6 meters per second. Zot's rover, with a mass of 170 kilograms, is traveling on the surface of Mars at 8 meters per second. Predict which rover has more kinetic energy. Then verify your prediction mathematically. You may now pause the program. So did you make the correct prediction? Let's double check your work. Solving for the kinetic energy of Norbert's rover, we have kinetic energy is equal to 1/2 times 210 kilograms times 6 meters per second quantity squared. The kinetic energy of Norbert's rover is equal to 3,780 joules. Solving for the kinetic energy of Zot's rover, we have kinetic energy is equal to 1/2 times 170 kilograms times 8 meters per second quantity squared. The kinetic energy of Zot's rover is equal to 5,440 joules. So, comparing the two values, we see that the kinetic energy for Zot's rover is greater than the kinetic energy for Norbert's rover. We now know that an object may possess both kinetic energy and potential energy at the same time. Let's go back to our example with the apple. Any object that rises and falls experiences a change in its kinetic and potential energy. Let's look at this energy transformation as I toss the apple into the air. When the apple moves, it possesses kinetic energy. As it rises, it slows down. Its kinetic energy decreases. Because the height increases, its potential energy increases. At the highest point, the apple actually stops moving. At this point, it no longer has kinetic energy, but it has maximum potential energy. As the apple falls, the kinetic energy increases and the potential energy decreases. No matter how energy is transformed or transferred, all of the energy is still present somewhere in one form or another. This statement is known as the law of conservation of energy. As long as you account for all the different forms of energy involved in any process, you will find that the total amount of energy never changes. In other words, energy cannot be created or destroyed. It just changes form.